Okay, for this video, we're going to be going over lesson 3.2, starting with the transmission of sound to the human ear.
Now we're going to talk about sound waves getting to human ear and how we hear it. So again, a vibration is what is the primary source of the sound waves, and anything that is vibrating is creating these waves, and they are going to move out in all directions through different media. And when vibration stops, the sound wave is no longer produced. So the sounds that you hear are all just different waves hitting your ear with different frequencies. So humans can hear sound waves that are 20 hertz to 20,000 hertz. So 20 waves per second. If a wave hits your ear at that rate, 20 waves per second, you're able to hear it. And all the way up to 20,000. Okay, that's a big range. That does get smaller as you get older, but if you're young and you have perfect hearing, 20 to 20,000. So 20,000 waves per second, your ear can handle figuring out what that is. So that's just the human range of hearing. That doesn't mean that sound waves don't exist outside of that range. We just can't hear them as sound waves. Our ears and brains don't know what to do with them. So there's other animals that can. For example, bats use echolocation. They make sounds that are too high pitched for us to hear, but then they can hear those sounds that they're making. And a dog whistle is a whistle where you blow on it and you don't hear anything. It sounds silent to you, but the dog can hear it perfectly because it's such a very high pitch. So there are sounds higher and lower than we can hear, and humans actually have a use for some of them. So frequencies higher than that range, higher than 20,000 hertz, are called ultrasonic. And we use those for some things. Sonar, so you have boats sending out sound waves into the ocean or even into a lake. If you have a fish finder that's using sonar, it's sending out the sound waves. They're bouncing off of stuff in the water and coming back. And we can't hear the sound waves, but we have machines that can hear it for us. So the machines pick up that data and tell us, what's going on based on the sound waves that bounce back. Some industries use sound waves for cleaning equipment, basically just vibrates it so much that the dust falls off, and for detecting holes and flaws in equipment. So again, those are sounds that are too high of a frequency for us to hear. And medical imaging, so ultrasounds. Um, the name ultrasound comes from ultrasonic waves. So these images are actually just created by sending out ultrasonic waves into the body, so sound waves that are at a pitch too high for us to hear, but we have the computers that can take the data from those sound waves as they go through you and turn it into images. So they're taking the data from the sound waves and converting it into a pattern that we can see as an image. So that's what ultrasounds are. Sounds that are lower than human hearing range, so anything lower than 20 hertz, 20 waves per second, we can't hear it. Um, those are called infrasonic. And we don't really have uses for infrasonic waves the way that we do for ultrasonic waves.
Now, when we hear changes in frequency, we hear that as changes in pitch. So you can think of a high-pitched sound and a low-pitched sound. Those are things that are going to be different frequencies. A high-pitched sound has a high frequency, and a low-pitched sound has a low frequency. I'm going to play some examples, and I want to stress that it's just the pitch, and that has nothing to do with how loud the sound is. So volume or amplitude is completely separate. So this is going to be a sound that has a high pitch. This is about 5,000 hertz. And then this next one will be a little less painful. I'm hoping the sound comes through the speakers correctly. This is a bit lower. This is 850 hertz. So those are two different frequencies. So we hear a high pitch and a lower pitch. And those have nothing at all to do with volume. So what I'm going to do is play this lower one again, the 850 hertz, and change the volume, and you could hear that it gets louder and quieter, but the pitch doesn't change. Okay, so here we go with that. So I turned the volume down, I turned it back up. It changed the amplitude of the wave, but it didn't change the pitch at all.
Okay. So sound cannot travel at all through a vacuum. A vacuum is an empty space with no molecules in it, like outer space. So in outer space, it's true, no one can hear you scream or any other sounds. You can't hear anything in space because there's no sound waves able to travel through it. So in movies where, let's say there's space battles and you see things crashing and colliding and there's explosions, all of those things you think would make sounds. And if you are somewhere with an atmosphere, they do. And if there's people inside the spaceships where they have air in there, it's going to be very loud. But if you're outside and you're in space, you can't hear any of that happening. It would all just be perfectly silent. Okay? So it's kind of weird. Um, what sound needs to be able to move, like we talked about, is the molecules so that it can make that chain reaction happen where it bumps the molecules in front of it and those bump the molecules in front of that. So the name in general for that is a medium. A medium is anything that has molecules where the sound waves can make the molecules bump into each other and progress the sound wave from one point to another. Okay, so the molecules that they travel through is called a medium.
Now, sound travels through anything with molecules, but different types of substances are going to work better. So, if sound travels through a medium, the best thing it could go through is an elastic solid. And elastic means the molecules kind of snap back really quickly. So, things that are elastic in this way are things like metals. They're really good elastic solids. The molecules kind of move real quickly, pop back to where they're supposed to be as the sound wave goes through them. Inelastic solids are not as good. So that might be things like cloth fabric, where the sound wave hits them and it doesn't really pop back as easily. Liquid is the next best, and then gas is the worst. So solids are really fast. Elastic is even faster than inelastic. Liquids kind of in the middle, and then solids are really slow. And we have the term insulators. So insulators for sound are materials that don't let sound pass through them very easily. And some examples of that we'll talk about soon. Um, but first I want to go over sound waves and moving through things still. So um, when you have something making a sound, the wave actually pushes out from them in all directions. And it makes a compression, and behind it is a rarefaction. But that compression is a sphere shape around the thing that's making a sound. And it just spreads out away from them. And as the sound wave keeps going, each compression makes another sphere shape behind it. So those sphere shapes are called wave fronts. Okay, they're just circles or spheres around the object that's making the sound. And it's the compressions of the sound waves, one right after another. Now, there's only a certain amount of energy in each wavefront as it starts, and then it moves out and it gets bigger. So it's kind of being stretched out, and the amount of energy in each one reduces as it gets farther away. And this is what we measure as the wave's intensity. So wave intensity is the amount of energy in the wavefront, and it depends mainly on amplitude, but also on distance from the source. So as a wave spreads out, its intensity decreases as the area that it covers increases. Okay, so again, it's just like being more spread out. It's getting stretched thin. It's taking up a bigger area, so it's less intense. And the formula that we have for that is 1 over r squared, where r is the distance from the source. So if you have something that's making sound, you get a sound wave that comes out of it, and it starts off kind of intense, but then as it spreads further away, it takes up more space and it gets less and less intense. You can see it kind of fading in this diagram here. And the way that we measure that, again, is with this formula. And as the distance changes, the sound wave intensity changes. So as it gets 2 times as far away, we put 2 into the formula there for R. So we had 1 over R squared. So we have 1 over 2 squared because it's twice as far away. And then we just do the math there. So 2 to the second power is 4. So our change is 1/4. So if it's twice as far away, it's 1/4 as intense. And if it's 3 times as far away, the intensity is only 1/9. If it's 4 times the distance away, the intensity is 1/16. And if it's 5 times, the intensity is 1/25.
And the way that you actually hear sound is your ears kind of collect the sound, go through the middle ear, and there the eardrum vibrates with the same frequency as the waves that hit it. So remember, you can hear sounds of up to 20,000 hertz. So that means your eardrum can be vibrating 20,000 times a second. It's crazy. That frequency goes to the inner ear. It's repeated as it goes through different bones in your ear, and the auditory nerve picks up on that pattern and sends that pattern to the brain. And one thing that's kind of interesting is how we can tell whether a sound is coming from your left side or your right side. The sound is going to reach your ears slightly differently. So if the sound is on your right, well, let's say the sound is okay, well, whatever. If the sound is on one side, the sound will be slightly louder on that side, but it'll also hit that ear first. And a very small difference. Your head is not very big, and sound moves very fast, but it's still enough of a difference for your ears and brain to recognize that difference. So the sound reaches you on one side, and your auditory nerve sends the signals to your brain, and they're going to be just slightly out of phase. So it's going to say, oh, your left side was first, or oh, your right side was first, and your brain will interpret that as the sound is coming from your left side, or the sound is coming from your right side. And sound wave characteristics is what we're going to finish with today. So reflection is pretty important. Waves that strike a smooth, hard surface are reflected. And when waves are reflected, they don't change. The frequency stays the same and the wavelength stays the same. They never change. And the other thing that doesn't change is the angle. So if you have a wave hitting a surface at a 30-degree angle, it reflects at a 30-degree angle. The incident wave is 82 degrees. It's going to reflect at 82 degrees. So the way that we write this is by saying the angle of incidence, so that's the angle that it hits the surface at, okay, the angle of incidence is always equal to the angle of reflection. And when sound waves are reflected, and you hear the sound wave and then it hits another surface and it comes back to you a second time, that's what we call an echo, so it's probably something you're familiar with. And we can actually figure out what it takes to hear an echo. So you need enough time for the sound to hit you once, and your ear to register that the sound stopped, and then another sound is coming back and hitting you, and that it's a separate sound. So your ear needs a little bit of reset time to figure that out. So it's got to be at least 0.1 seconds. So you need to be far enough away, because if you're less than that distance away and it takes less than 0.1 seconds, the sound wave hits you so fast that you can't tell it was different. But if you're far enough away, you have enough time to recognize that it's an echo, that it's a separate sound than the first one that went by you. And mathematically, we can figure out that distance. It's at least 16.6 meters. So based on this idea here that you need at least 0.1 seconds for your ear and brain to interpret it as, okay, the first sound finished, now we have another sound. And based on the speed of sound, it takes 16.6 meters to put enough distance between you that the sound will travel there and travel back, taking enough time for your brain to experience it as an echo. So that's one of the questions in your review, which is just explain the conditions which a person can or can't hear an echo. And it's really just two things. You need a surface for the sound to reflect off of after it's passed you the first time, and you need to be at least 16.6 meters away. Because if you're closer than that, it happens so fast you can't possibly hear that the echo is happening. You just think it's one really long sound. Um, so we're talking about reflection, but also sound waves can be absorbed by a porous surface. So it means a surface that has a lot of holes in it. And the amount that that happens is different for different materials. So some materials absorb sound really well. They absorb a high percentage of the sound that hits them. Other materials are not, and they absorb a lower percentage. So your book describes this and gives you this chart of coefficients of absorption. So you look in your text and you'll see this chart, and it's got some pretty specific materials, but it tells you the percentage of sound waves that are absorbed when these materials are hit with sound waves. So the top one is something that is designed just for this purpose. Okay, acoustic ceiling material is for soaking up sound waves. So in office buildings and public places where they don't want it to get too loud in there, they'll have these ceiling tiles that absorb the sound waves instead of bouncing them back down at you. So the coefficient of absorption is 60%. That means 60% of the sound waves that hit this material get absorbed instead of reflected back. As opposed to other things, so for example, wood is only 5%. So of all of the sound waves that hit a wall made of wood, only 5% of them get absorbed and the rest get bounced back. So you're going to see questions like this. So which of the following materials would be the least efficient in soundproofing a room? So for soundproofing, you want it to absorb that sound so it can't go anywhere else. Okay, so you're going to go back to your chart. This one was the best one, perforated acoustic ceiling material, and your other options were plaster and clay. So you can see those are both at 3%. So they only absorb 3% of the sound, so they're pretty bad. And that's actually what your question is asking, is which is the least efficient. So it's actually a tie between clay and plaster because they were both 3%. So if you do see this on your test, there won't be a tie. There'll be ones where there's a specific one answer. But make sure you look at the chart to get your actual numbers. So if you see anything about absorbing sound waves or soundproofing or coefficient of absorption, make sure you go back to your text and look at this chart. So that is when sounds hit solid objects. You could also have effects when sounds go from one medium into another and keep going. So refraction happens when a wave passes from one medium to another, which changes the velocity of the wave and makes the wave bend. So for example, if you're underwater and somebody out in the air makes a sound, that sound wave goes through the air, goes into the water, and then you hear it. But on its way, it's slowed down, and that's actually going to bend the direction. It's going to change the direction that the sound wave is moving. So another thing that causes these refraction is actually changes in layers of air temperature. So cold air is more dense than warm air. So if sound moves from warm air into cold air, it's kind of like it's moving from one medium into a completely different medium. It's moving from less dense, or yeah, less dense to more dense. So it's going to actually change speed. Okay, so here's a little example of how that works. On a hot day, the air near the ground is warmer, the air in the atmosphere is colder. So as the sound moves from the cold atmosphere down to the warm, it's actually going to refract upwards. It's going to change direction and bend upwards. And on a cold night, the reverse would happen. So if the air is actually warmer above and you get cold air on the ground, it would do the opposite and refract downward. And as sound goes through a crack in a barrier, you get something called diffraction. So diffraction is that the sound waves will kind of go around the edges and bend, and spread out on the other side. And so they're going to fill the space on the other side of the barrier. So I'll bring up an animation in a second, but you're going to think of, like, say you've got a soundproof wall that has a doorway in it. So as the sound hits the wall, it would get absorbed, so the sound can only go through the doorway. So the question is, what happens on the other side of the doorway? Can you only hear the sound if you're standing right in front of it? Well, what happens is your sound waves hit, they will only go through that doorway, but then they bend. So they go off to the right, and they go off to the left. So you can hear this sound from anywhere on this side, even though the sound was only able to get through this tiny spot. Okay, so if someone's standing here and they're speaking, and somebody is all the way over here, even though the sound was only able to get through this tiny area right here, it spreads out as it gets around that gap, and so somebody standing over here will still be able to hear them because the sound waves will go off in that direction. And some will go off in that direction, and that direction, and that direction, and they're just going to spread out and fill out the whole room. So that's called diffraction. So refraction is the sound waves bending as it goes from one material to another, and diffraction is sound waves bending as they go around the edge of a barrier. All right, so that's all that I'm going to present at the moment. We do still have a few minutes to ask questions, so I don't see any questions that came in while I was talking, but if you have any questions now, you can definitely type the questions that you have. And if you have any questions later, or if you're watching this recording afterward, here's how you can get in touch with your instructors.